Okay, we're going to talk about when we have an applied force that's at an angle. Okay, so this is similar to our tabletop scenario, like these, where our applied force was parallel to a surface. But instead, we're going to have an applied force at an angle. So it's going to look something like this. So we're still on a horizontal surface. Let's see, we've got friction in this example. We've still got force of gravity. Still got normal force from the surface. But now we've also got two components of the applied force, because we've got a horizontal component and a vertical component, because we're pulling at an angle. So this is really a combined horizontal and vertical applied force. Okay. So that changes a couple of things in our scenario. We can still get force of gravity the same way. That's still m times g. So in this scenario, we've got a 10 kilogram box. It's being pushed with an applied force at an angle. So we've got a value for that angle and that combined applied force vector. And then we've got a mu value here. So we know we've got friction. Okay, so calculating individual forces first. Force of gravity is going to be 10 times 9.8, so 98 newtons. My applied force, I've got two components. Okay, so I've got my x component. That's going to be my combined vector here, which is my hypotenuse of this right triangle that I've made here. Okay, so this x component is going to be the hypotenuse times cosine of my angle, and that's this angle right here. So cosine of 25, and 50 is my combined. So I've got 50 times cosine 25 gives me, always make sure you're in degrees, gives me 45.3 newtons. And then my y component of my applied force is going to be the same hypotenuse, this combined vector times the sine of my angle, since that's my opposite side. So 50 times sine of 25 is 21.1. Okay. Okay. So then I know that my force of gravity is being offset by both normal force and Fay, because these two vectors are pointing in the opposite direction of force of gravity. And in this case, this object is not moving vertically. Okay, it's just on a surface. So my vertical force is my F net in my vertical direction is balanced. It's 0. So that means Fg equals Fn plus Fay. And then I can use that to help me get normal force, which is Fn equals Fg minus Fay. I'm just moving this one over, subtracting it from both sides, basically, so I can solve for Fn. And that's going to give me 98 as my Fg, minus 21.1 was my Fay. So 98 minus 21.1 is 70. I'm just going to round to 77 newtons. Okay. Then I can get my force of friction. I'm running out of room here. That's mu times my normal force. And that is 0.35 is what's given here for mu times my normal force I just figured was 77 newtons. So let's see, 0.35 times 77 is, again, I'm going to round. I got 26.95. I'm going to round to 27 newtons. Okay. So now I've gotten everything vertically. I know these are balanced. So I know that my F net and my acceleration are happening in the X direction. Okay. Because that's where my movement is. My box is being pushed across this surface. And so I know that my F net is going to end up being FAX minus FF. So I've got FAX in one direction, I've got FF in the other. Okay. And I always take an absolute value for force magnitude. So I've got 45.3 is my larger, that's my FAX. And I'm going to subtract from that my 27 newtons I got for force of friction. (27) is 18.3 newtons. Okay, that's my F net. That's the vector sum of the forces acting on my object that are causing it to have motion. Okay, so I have a vector sum vertically that's 0 because I'm not moving up and down vertically. But horizontally, I'm moving across the surface. So I've got an F net in that direction, and that's my vector sum of FAX and FF. And if I want to get acceleration, that's my last step. I'm going to do F net divided by my mass, because here I'm just using F net equals mass times acceleration. That's my, you can see it right at the top up here, my Newton's second law equation. And that's going to give me, I could do that in my head, 1.83 meters per second per second. Hopefully y'all can read this when I scan it. All right, and then I've got one other example on here. This one's simpler because it says there's no friction. Yay, that's always nice. So we're pulling a box by a rope. It's a 25 kilogram box. Tension force, that's my applied force in this case, is 100 newtons, 38-degree angle. So most of the same steps here. I'm just going to reference this free body diagram because I don't have a lot of room. My force of gravity is going to be 25 times 9.8. Okay. Which should be about 250, right? Oops, I divided. 245 newtons. I'm going to go ahead and calculate my components. So I'm going to get my X component is this 100 newtons, my combined tension force of this rope. So 100 multiplied by cosine of 38. And remember, we're just choosing cosine because that's the adjacent side. So we're using our right triangle math there. Oops, what did I do? 100 times cosine of 38. 78.8 newtons. And then I'm going to get my FAY, which is 100 times sine of 38. And that's 61.6. Okay. And then my normal force, I'm going to go back to what I did earlier. It's going to be force of gravity minus that Y piece of the applied force. So 245 minus 61.6 gives me something 183.4. Okay. And I don't have friction. Okay. So actually my free body diagram is a little simpler in this one. I've got force of gravity, I've got normal, I've got my applied at an angle. And so then I've got those two components, and that's it. So all of my F net is going to be FAX. Okay, because I'm pulling on a surface with no friction. So there's nothing pulling back on this piece right here. So F net equals FAX equals 78.8 newtons. And then if I want acceleration, that's going to be 78.8. That's my F net divided by my mass was 25. 78.8 divided by 25 gives me 3.2. Just rounding there. 3.2 meters per second per second. So same way we did the other one, just a little bit simpler if you don't have to deal with friction. So, all right, next up will be elevators.